Hello everyone. So this video on knowledge structures and learning challenges is intended to support the phase 2 and 3 part of the professional development program for us in engineering in particular. And that's because the generic approaches to really unpacking what it is that students are struggling with don't really help us in the STEM areas. So we're going to take a little bit of a theorized view of what it is that students are learning and how they're learning so that you can actually address those challenges more effectively. Now, we're going to use some concepts from the sociology of education to unpack what we mean by knowledge. Now, some of this may sound very theoretical, but there are two important concepts to grasp. This comes from Basil Bernstein. Now, Bernstein talks about vertical and horizontal discourses. Now, vertical discourse is simply formalized educational knowledge. It's everything that we work with in the spaces in which we work. And horizontal discourse is everyday knowledge. Now, the problem is that the requirements of higher education have changed tremendously. If you look at all of our graduate attributes, you'll see that all of those elements are in fact based on the principle of exercising forms of knowledge and kinds of skills or practices in relation to society or in relation to particular professional fields. That means that in our teaching, we are constantly moving between what we call vertical and horizontal discourses. So we build good citizenship and good professionalism through modeling, in other words, learning from a social environment, but it must be based on a fundamental understanding that's implied in vertical discourse. Now, in vertical discourse, we have different kinds of knowledge structures. Now, the first structure and the most important is what we call hierarchical knowledge. Now, hierarchical knowledge simply is the kind of knowledge where concepts build on each other and add consistently. Physics is our classic hierarchical knowledge structure, and the other natural science areas. So the definition here is this is a knowledge structure which attempts to create very general propositions and theories which integrate knowledge at lower levels. We talk about a subsumptive progression of knowledge over time, where new theories or concepts extend and integrate earlier ones. Now, think about Ohm's law, for example. Ohm's law subsumes, absorbs the behavior of electrons, the nature of different conductors, principles of resistance, and so on. And it's reduced at its simplest to V equals IR. The example in the graphic over there is just force, for example. Okay? Now, this kind of knowledge takes a really long time to build, and it's integrated fairly sequentially in the school physics curriculum. Now, learning here is about strong sequencing. Each element must be grasped before the student can move on. You need to teach these elements explicitly, and you need to mediate at every single stage. Hierarchical knowledge structures require tools like mathematics or symbols or language or objects to demonstrate principles which describe the behavior of the physical world, whether at a nano or micro invisible level or whether at a physical level or at a visible level. Now, learning time. These types of knowledge take years to develop conceptual grasp. Now, if base sequential concepts are in place, principles can actually be grasped fairly quickly, and the periods of learning can become shorter and shorter. So, if, however, in terms of challenges, if base concepts are missing, then different kinds of interventions are necessary. Things like extra classes or winter school or revision of principles. Note that some of these principles can be elicited through actual experience. Now, to demonstrate understanding, in other words, to represent this understanding of this kind of knowledge, students require the use of other types of knowledge. They need language, symbols, graphics. Now, if the student doesn't grasp the appropriate forms of representation, these must also be explicitly taught. And here's the big challenge. Because they may not have the tools or understand how to use the tools to express their understanding, we may get confused. Is it the concept they're not getting, or is it the tool they're not getting? And that's an important thing that we need to identify when we address learning challenges. Now, the second knowledge structure type is called horizontal knowledge. Now, horizontal knowledge structures, and this is according to Bernstein, and I'm quoting, consist of a series of specialized languages with specialized modes of interrogation and criteria for construction. What that means is that there are kinds of knowledge structures where the same type has different languages. And each language has what Bernstein calls an explicit conceptual syntax, which is capable of precise or relatively precise empirical descriptions. To put it very simply, let's look at Pythagoras. Now, the theorem of Pythagoras is a squared plus b squared equals c squared has an explicit conceptual syntax. You see a squared plus b squared equals c squared, and you recognize it as mathematics. And you recognize that it empirically describes the lengths of the sides of a right-angled triangle. Now, each of these kinds of knowledge structures have multiple languages, and each of the languages, look at algebra, geometry, and trigonometry, has its own organizing principles, and learning of each of the types is a little bit similar to the learning of physics in that each type has its own rules internally that build on each other. The difference here is that there may be a different language of the same type to represent the same knowledge. An algebraic linear equation, for example, can be represented using coordinate geometry, but each has their own rules of syntax. Now, learning in these kinds of knowledge structures is slightly different. Each language and its own principles need to be learned independently. Now, sequencing is not as strong as in hierarchical knowledge, but principles need to be explicitly taught. The more languages acquired, the easier the learning of a new one. These kinds of knowledge are all the problem-solving tools that we talk about. They are languages used to analyze, manipulate, and explain phenomena, whether they're physical or social. There are often multiple approaches to applying this kind of knowledge. These kinds of knowledge need time to acquire the masses of particulars, and they need time to practice a range of application scenarios. A lot of this learning can also be done independently. Now, the types here, in case I didn't mention this before, this is mathematics, but this is also economics. Each paradigm, it's also politics, and law. Each paradigm, each type has its own rules, has its own kind of language. The big teaching and learning challenge here is the time for multiple types of application. Tutorials are ideal for this type of knowledge, where time is allowed to practice a range of approaches to solving problems. The grasp of procedural principles for each approach is also very important. Here is where understanding the appropriate form of representation and the conventions of that specific language are essential, and they must be explicitly taught. Sometimes group work is ideal for this type of knowledge. Now, this takes us to the third knowledge structure. It's also called horizontal knowledge, but it has what we call weak grammaticality and verticality. Quite simply, social sciences are generally classified as having a weak horizontal knowledge structure. And that is because, and I quote again, the capacity of the theory to stably identify its empirical correlates is weaker. In very simple terms, the same word could be used in multiple different languages. The word function, for example, it's in maths, it's in programming, it's in sociology, it's in chemistry. And it actually takes on different meanings in those different contexts. So you would have to define in which context. Now, Bernstein establishes that weak horizontal knowledge structures progress by way of proliferation and redundancy. Okay? There's a lot of cutting and copying and pasting from different kinds of knowledge areas. It changes over time, sometimes really rapidly. Now, we see this in information communication technologies. This is at the heart of computer-based engineering practice. Here, you will see that the different programming languages, they borrow terms from each other. They borrow syntax-related elements from each other. but each one has its own kind of rules and laws, and there's a lot of redundancy. Working with these kinds of knowledge structures means you constantly have to refresh your knowledge base. You have to adapt to new forms. You need to respond to a different set of organizing principles. Here, we do not have strong sequential learning as we have in the other cases. And here we have what's important is you would need to learn to apply these in multiple contexts. So, just to repeat, this is non-sequential accumulation of masses of particulars. It can be done very effectively independently. It requires access to a range of examples and comparisons. There are many variations or options for solving the same problem. You know, a combination of tools like mathematics, symbols, and language to analyze, describe, and manipulate social or man-made phenomena. These types of knowledge take time and resources, and ideally, students need access to the required resources on their own to be able to practice. And trial and error works really well here. The big challenge is time and tools. Students need flexibility with regard to pace. They acquire this kind of knowledge in many different ways and at different rates because they also draw on their own conceptions of what the purpose of the tool is and how it is that they actually learn. Application here requires the combination of other types of knowledge, language, symbols, graphics, and if a student doesn't grasp the appropriate forms of representation, these must also be explicitly taught. Now, this is just an example from my own research on what happens in engineering. What happens when you integrate the different kinds of knowledge structures? Now, this example, as you see, is probably relevant to all of us, although this is because of my focus in my PhD on mechatronics, engineering problem solving. The problem is that, as you can see, if you separate out the different kinds of disciplines, they have different kinds of rules, different kinds of learning that is required, different kinds of allocation of time and resources. Now imagine when we throw that project at a student and we're trying to identify, well, where is the student actually struggling? We might easily talk about, well, time management, or talk about their inability to write a report, or quite possibly their inability to apply a particular tool, like a software program or mathematics. But hidden beneath that, and the reason that I've covered these knowledge structures with you, you would have to really zoom in to be able to identify what exactly is it that students are not coping with. Right. When you've zoomed in, what you might actually find is that it's a fundamental, what we call a threshold concept that students are not grasping. Now, a threshold concept is like passing through a portal. It's a conceptual gateway that opens up previously inaccessible ways of thinking about something. So this comes from Mayer and Land. Now, on mastering a threshold concept, the learner begins to think, as does a professional in that discipline, and not simply as a student in that discipline. The learner begins to think like an engineer, or like a chemist, or like an economist. In other words, grasping a threshold concept involves an ontological, that means a sense of self within themselves, as well as a conceptual shift. Now, threshold concept examples, there are several, okay? And a classic one, for example, is temperature gradient in thermodynamics. And there is an example over here that you can take a look at. There are other examples like opportunity cost in economics, or gravity in physics and engineering, depreciation in accounting, deconstruction for text analysis in English literature. The point here is a threshold concept is the place where students get stuck. And our challenge is how to see what it is that they're getting stuck with and how to overcome it. If we can't identify the fundamental threshold concepts and we consistently experience students struggling with their learning, then we're going round and round in circles. So the key in the tasks that you're busy doing, and in our teaching and learning in general, is to be able to zoom in and see what is it that is actually challenging the students. Now, some of the characteristics of a threshold concept are that they are transformative. a shift occurs in the learner's perceptions. This is that aha moment that you experience in a class when you see it in somebody's eyes. This is that I can suddenly see moment. And this brings us to the second one. Threshold concepts, when we pass through that portal, they are irreversible. You can never unsee something once you've seen it. The third characteristic is that they're integrative. Once you see something, it exposes the interrelatedness in a subject area or in a discipline or in a field. It enables students to begin to coherently integrate what were previously seen as unrelated aspects of a particular subject. And I think this is the problem that many engineering lecturers face. There is so much siloed teaching. There is not enough linking across into other knowledge areas or into other subject areas or into the field of application. And if a student has really grasped a concept, they will be able to make that shift more easily. The fourth characteristic is that threshold concepts are bounded, bordering with other thresholds or new conceptual spaces. The more interdisciplinary a subject, the more complex it's actually going to be to enable them to see the links between others. Now, troublesome knowledge, these are the traditionally difficult concepts. They may include concepts that either clash or compete or interact in ways that appear illogical or unfamiliar or alien to students. It is our job to identify what those troublesome knowledge elements are. So as you go through the task of unpacking your module, looking at, or a part of it, looking at what it is that students are really struggling with, I want to challenge you to think about this at the really micro level, at a theorized level. First of all, what kind of knowledge area is it that you're working in? Secondly, is it the concept or the tool or the form of representation that students are struggling with? The point is that when you've identified these things, we are all subservient to what Biggs calls the principle of constructive alignment. We need to understand that students construct their learning in ways that sorry everyone, I've got a whole lot of notifications coming in here. That students construct their learning based on what you intend as learning outcomes, how you include appropriate learning activities which are aligned to how you're going to assess them according to the assessment criteria. Now, we're going to work on assessment and outcomes at a later date, but I just want to remind you that your job here is to identify the gap appropriately.